Hi there and welcome to a calculus video where we will introduce sequences and series. And in this video, we will focus on what a series can do for us, what it means, and all the vocabulary along with it, so that as you begin your unit with sequences, you have a much deeper foundation of where you are headed and what this is going to mean for you in the long run. Okay, so you may have been given a sheet like this to use, or you might in the future, which is a list of all of the MacLaurin series that we know, or at least the most commonly used. So for example, we have a series for 1 over 1 minus x, 1 over 1 plus x, the series for e to the x. But what I'm going to look at right now and talk about so you can really get a much deeper understanding of where we're headed is the series for sine of x. So again, you can kind of see why we're studying both the sequences and the series. So I'm going to rewrite sine of x over to the side so we can discuss some vocabulary around this. Okay, so what I have here is the series for sine of x, and if you'll look, there's sort of three pieces here. There's the left-hand side, there's this middle area, and then of course there's the right-hand side. So each one is a unique form or representation of the same thing. So for example, sine of x is the function form. You've been studying f of x equals sine of x for a very long time. So we recognize that. In the middle here, you have this expanded series notation or an expanded power series. And the reason I'm going to call it a power series is because if you check this out, everything is just simply a power of x. I'll talk about that exclamation point here in a minute. So it's an expanded power series. And again, I'll show you graphically what that means as well. And then on the right-hand side, we have this summation notation, which will show us the pattern of how to get any term along with the sigma in front gives us the sum of those terms. So there will be different times throughout your math career where you may want to just look at the function f of x equals sine of x. There are certainly times where you will want that expanded power series notation. And there are also times where the summation notation will be very helpful because you're summing up an infinite amount of terms. So let's start with basics. So you may have never seen that exclamation point before. So that is a factorial. So for example, 3 factorial is really 3 times 2 times 1, or we could certainly write 6. Now the reason we don't write 6 is because we can hopefully see the pattern. See, I have an increase of 2 each time where it's all of the odds. So 5 factorial, for example, would be 5 times 4 times 3 times 2 times 1, and that should be 120. So the factorial says that's the largest number in that product, and it decreases by 1. So 5 times 4 times 3 times 2 until you get to 1. You will see this a lot in combinations and permutations, or in other words, in probability. So if you've done a probability unit in a stats course or in another course, you might have seen this before as well. So 0 factorial is defined to be a 1 because 1 is what we would call a multiplicative identity. It is always there. We can say a number is unchanged when it's multiplied by 1. So for example, I don't have to say 1x, although I certainly could, because if I multiply it by 1, it's unchanged. Okay, so what else should we know about this? Well, if we want to represent an even number, it should make sense to you that that's probably 2n. Okay, so therefore, if I want to represent an odd number, it's always 1 away from that even, whether it's 1 additional or whether it's 1 less. So it could be 2n plus 1, or we could represent it as 2n minus 1. Okay, we also have an alternating condition. Again, I'm going to use notation that I hope will help you later on with your series divergence or convergence. So this alternating condition, I am going to call this negative 1 to the n, that alternating condition. And we could also represent that as to the n plus 1. We could say it was to the n minus 1, depending on what we need. But for our purposes in this sine of x, we have this negative 1 to the n. That's an alternating condition because if my exponent is odd, then -1 to the odd would be negative. If it's even, a -1 to an even number, like -1 quantity squared, -1 to the fourth, etc., would be positive. So that's going to make this alternate, and I can see that here in my expanded power series. My first term is positive, negative, positive, negative, positive, negative, and it will continue to alternate. So that's what that alternating condition looks like. So let's take a look at this graphically to see what we're looking at. Okay, so what we're looking at here is the graph of f of x equals sine of x is graphed in red. And all I did was type in the first two terms of that expanded power series notation, which was x minus x to the third over 3 factorial. And what you're going to notice is, at 0, 0, they're actually both exactly the same. Both functions cross through 0, 0. And what you might notice also is that the red and the green curve are really, really close together, between 0 and maybe 1. So for example, f of 0.1 and h of 0.1, that's what I named my functions, as decimals are accurate to, what is that? 3, 3, so 1, 2, 3, 4, 5, 6 places already. And I've only written out 2 terms of this MacLaurin series, which makes it very, very good approximation at 0, in this case exact. They both cross through 0, 0. And anything kind of zoomed in on this area, it's a very good approximation for sine of x. So what would happen if I include more terms of that MacLaurin series? So let me do that. Let me put that in there. So now I'm going to call that g. So I have x minus x to the third over 3 factorial plus x to the fifth over 5 factorial, etc. And in this case, I typed out, let's see, how far did I go? To 15. So x to the 15th over 15 factorial. So 1, 2, 3, 4, 5, 6, 7, 8 terms. Okay, so I only have 8 terms that I'm looking at. Now keep in mind, the actual MacLaurin series has an infinite number of terms. Well, what I hope you see here is if I just look at one cycle for sine of x, 0 to 2 pi, these curves are really, really close together. And if I turn off the green, you can see the red, right? So here's sine of x. Here's my MacLaurin series representing sine of x. Look at f of 0.1 and g of 0.1 now. They are accurate, gosh, all the way out, however many decimals this shows me. So I can be accurate very, very quickly because the first one, I only used 2 terms. I was accurate to many places right away. If our desired level of accuracy is only 1/100th or 1/1000th, I might not need that many terms. And I can just use a power series instead of this trigonometric function. Now, why can that be helpful to us? Its derivative is easier, power series. So think about it. What kind of derivative are you doing when it's a power of x? You're doing power rule. What kind of antiderivative would you be doing on that power series? Power rule. So it becomes very, very accurate. So it's a good approximation for this numerically, very quickly. And again, I'm not using that many terms. If you think about this having an infinite number of terms, I'm using less than 10 of them. So the MacLaurin series is giving you the most accurate approximation closest to 0. So we can see that. So the farther we get away from 0, it's not necessarily that good of an approximation, right? So if I'm trying to approximate f of 15, okay, this isn't going to be that good yet. But there's also a generalized Taylor series. MacLaurin is a very specific one, but a Taylor series, you can center your approximation around anywhere you want. So you could get an almost perfect, accurate estimation around 15 if you center your series around 15. So just horizontally shift this over. So what we're going to be talking about this chapter is basically these series and their 3 different representations. So again, I have that function representation, f of x equals sine of x. I have its expanded power series notation. And then I also have this summation notation, which we're going to work in for quite a while as well. So I have three different notations that are all going to be the same numerical approximations. And the last thing I'll show you is that I did type in this summation notation, and you get the summation a few different ways, but you can also just type SUM or sum into your Desmos website. And we were starting at n equals 0. That's the starting point of this. Initially, this was going to infinity, but again, I can sometimes see where I'm headed at 100 or 1,000 or 10,000 or 100,000. So we can work through terms like that. -1 to the n, x to the 2n plus 1 over 2n plus 1 quantity factorial. So it was basically x to the odd over that same odd number factorial. And you can see that this is almost a perfect trace here of my sine function. So again, I hope you found this video as an introduction just helpful. The first thing that you're going to look at is a sequence, which is just a list of numbers, but hopefully you have a little bit more vocabulary and maybe a deeper understanding of why we want to study infinite series altogether. I hope you found this video helpful. Thanks for watching.